Question 20. Okay, plastic beaker is placed in a microwave oven. The beaker has a mass of 0.2 kilograms. Specific heat capacity of the plastic is this. The water has a mass of 0.6 kilograms and its specific heat capacity is that. The energy is initially absorbed by the water, which then heats the plastic beaker. The plastic beaker and the water experience different temperature rises. The plastic beaker gains that amount of energy and the water gains that amount of energy. Calculate the temperature rise of the water and the temperature rise of the plastic beaker. Sounds like a horrendous experiment, okay? We've got a beaker and it's got some water in it and we heat it and one heats up more than the other. So really what we're looking at is just two questions. One is about putting some energy into plastic. So, actually let's do them in the right order. Water. Putting some energy into the water with its specific heat capacity and working out the temperature rise. We've got the mass of the water. And the second one is putting energy into the plastic. There's a certain mass of plastic and it has a specific heat capacity. That's just two equations or two questions with basically the same equation. It's an equation you need to remember that it exists, but you don't actually need to remember it because it says change in thermal energy is mass times specific heat capacity times change in temperature. It's not a change in state, okay? It's the one that's talking about change in temperature. So it's this one. So it is energy equals mass times specific heat capacity, which I'm going to put as C, times delta T. Okay, well we want the temperature rise of the beaker and the temperature rise of the water, so we want delta T. So if we rearrange that, delta T is E divided by M times C multiplied together. If we had it as a triangle, a bit one of those weird triangles, we've got E equals MC delta T. Okay, so all those bits are on the bottom. To find delta T, you put your finger over the delta T and it's E over MC is what's left. Not an ideal triangle. It's better if you can learn how to do it that way. So the change in temperature is the energy. Well, the water gains 151,200, 151,200, divided by, and then it's M times C. The mass, 0.6, times 4,200. Okay, so let's do that. It is 151,200 divided by, and then I'm going to put together 0.6 times 4,200. Okay, and let's see the answer. We get 60. So the answer is 60 degrees C. It's a bit of a shame that the formatting has gone a bit weird there and there's not much room to write. Okay, same thing here. It's just a different set of numbers. It's only 2 marks for this whole bit. That's a bit of a shame. Okay, because it's quite a bit of a long bit of question. Delta T it's the same equation, the energy divided by the mass and the specific heat capacity multiplied together, but this time it's the one for the beaker. So it's the beaker 13440 divided by, and then it's these two multiplied together, 0.2 mass times heat capacity 1680. 1680. Let's do that one. 13440 divided by, and then these two together, 0.2 times 1680, which is 40. So it's 40 degrees C. Oops, they've already got degrees C. Let's just check that. The water and then the beaker, and it actually says they have different temperature rises. The energy first goes into the water and then that heats the beaker. So the chances are the water is going to get hotter than the beaker. The temperature rise of the water is 60, temperature rise of the beaker is 40. That looks like it makes sense.